Two things landed this week. The DeepSeek updated V4 Flash, and we also get support for DSpark on llama.cpp. So today we'll be running it here, the 2084 billion parameter model on one RTX PRO 6000 with offload to RAM. And first we'll explain how it works compared to other speculative decoding techniques covered on this channel. Then we'll deploy it with one click, benchmark it to see whether DSpark is worth it even when you can't fit the full model. I'm Łukasz, a senior AI engineer specializing in inference optimization. Now let's get into it. Now let's look at DSpark, the DFlash grown up. So DeepSeek took the drafter we covered last time, fixed its two remaining problems, and now it serves DeepSeek V4 in production, and still it's loseless. So why DFlash draft fall apart after a few tokens and the tiny fix they applied? This is what we'll look into. Verify smarter no longer, so confidence scheduled verification. Then real production numbers with live traffic. So they notice 60 to 85% faster per user output, and whether you can run off any of it in llama.cpp and how to do it. So the longer draft survive. Let's look at the benchmarks from the paper. And as we can see, the green we have Eagle 3, and in the blue we have DFlash. So this is parallel speculative decoding, and then we have DSpark. And as we can see, in all of these benchmarks, we achieve higher results. And it varies because there are specific caveats to speculative decoding that we'll look into. Now, before DFlash, let's look at the MTP. We have the target model, and then it has hidden features of several layers, and we draft tokens using the MTP Eagle. So let's look at what actually goes into this head, because this notation matters. So it takes H, which is the target model last layer hidden state. So it's not text, not probability, but the vector that big model computed while reading everything so far. You can think of it as a target compressed read of the context. And what it believes the sentence is doing right before it commits of a word is E of T0. It's embedding of the token, the target just decoded. So the heads get the target understanding and the target most recent word. So this is the input then, yeah? And then we loop. So we have head for sequential passes, and every token awaits for the one before it. That's why we say it's autoregressive. Draft token 1 is embedded, and then fed back for token 2, then for token 3, and so on. And then we decide that, for example, we discard the third one. We'll accept 3 tokens and discard 1. And then we keep the prefix, plus we add 1 free bonus token because we're running in a decode step. So we can compute the token at the place that we reject. So this allows us to have a good quality because each token see the one before it, so the draft stays coherent, but it's bad latency because each token costs us the pass. So the drafter can become the bottleneck. Now DFlash cut the chain. Now there's extension of this, which is a DFlash. First, every round we start at the target, we hands the draft, its hidden state, and the last token it decoded, the anchor, and the drafter fills the rest of the row with a mask, like here. And because the DFlash allow a parallel drafter, instead of guessing future tokens one at a time, we propose a whole block in a single forward pass. So we saw it, and as we see, we generate all of these tokens in a single pass. So drafting cost is basically flat in block size, and it's conditioned on the big model internal state, the hash injected into every layer, which is why it can afford to be deep and smart. This we covered in other video in detail, so you can check it out. And as we can see, we get the target one pass, so we get the longest prefix, but as we see, it's only 3 here, so we reject the rest of the tokens that we still computed, and then we keep the prefix plus 1 free bonus token from the decode step. And as we can see, there is 2 cracks. First is that the draft tokens are predicted independently, as we saw here, so they can't see each other, so the quality will collapse at the end, as we could predict, and it was also mentioned in the paper. And 2, it verifies everything that it drafts. So even these tokens that we know are garbage will be verified. So we lose a real capacity that is very important while serving the model for thousands of users. And DeepSpark is the one that fixes each of these caveats. Before the fix, one picture that will explain us where each drafter breaks. We have acceptance by position, and we have acceptance rate on the y-axis and position the drafted block in x-axis. As we can see, the DFlash starts high. It's because of the anchor and its deep backbone. We make the great first guesses, but then we decay along the block as collisions pile up. Then we have the eagle tree. So it's auto-regressive drafter. It starts low. It's a shallow one-layer model, but it climbs up because each token sees the one before the draft. And each architecture is good at one end of the block. So we obviously want both ends. Here is the failure in one example. Context, sure, and of course, and no problem. Both are scored in the same forward pass. So when position 2 is scored, position 1 is still the mask. So it can only answer the vaguer question, what usually sits here, average over every way the slot before it might turn out. Now, both argmax fire at once, and neither one is wrong because they only consider the position they currently are. So we get sure of problem, and no sentence in English says that. The target rejects two positions, and acceptance is a prefix. So every token drafter behind it dies, just like this. So we basically discard a lot. So 4 perfectly reasonable tokens go into the bin because of the collision of these two slots earlier. So you could ask, why not just make the drafter deeper and get better guesses at position 2? Well, because the dev cannot fix it. Let's look at the arithmetic. We have position 1 with off and position 1 for no, and there is percentage 42 and 4. In the off word, position 2 is 50% course and position and problem is 1%. In the word of no, it's 85% for problem and only 1% for a core. That right hand panel U2 is the score vector, which is the backbone produced for position 2 in its single parallel pass. It is the only opinion position 2 ever had. Now let's look where the score came from. We have the left factor, which is the word, and by the word we see P of, and this is this case. So we have 42% here, and then 55% for the word course. Yeah. Then of word no, we have 40% multiplied by again the word course, which is 1. So that's how we get this percent. Right factor is the which word inside that word. Yeah, I know it sounds a bit complex, but bear with me. Let's now look at the score. 99% of problem score comes from the branch that actually loses at position 1, but it boosts the score here. So we have a sharp but unlikely branch that beats a blurry but likely one in the average because we wanted to have sure of course, not sure of problem, but it wins because of math in this technique. This is not a weak model, it's right answer at the wrong questions. So here is the fix, and it's smaller than you would expect. We keep the backbone and we add one wire. So every position ends up with two numbers added together. And what are these numbers? Well, first U is what the backbone wrote. It's a score for every word in a vocabulary written by the backbone in the parallel pass. So it sees the prompt, the anchor token, and it's blind to what position one sample. So we run this block 100 times, and U2 is identical for all the 100 ones. So you can see it here. There are the logits, and this is the score. And then we have B, which is the nudge. This knows exactly one thing, the token that just got sampled at the position before. It's a learned table of what tends to follow what. So we get one word, and on the out, we have one number for every word that could come next. So this is B. This is like a bias or the nudge as in the paper. And basically what we'll do is we'll add it. So if we just sample off, so the row for the off say push course up and push problem down. So as we see, we get additional scores because of course have more sense than of problem. And this see the off before and this score done. And then we, of course, get the total score of this addition. So U knows everything outside the block. B is the only thing that knows anything inside it. Let's now look at the whole round on one screen. So we start at the bottom left. We have marker 1 and the target model run one ordinary step. The context ends as A and it produces matter. This will be our anchor. Yeah, the arrows are a bit screwed here, but yeah, this means that it's from the full block basically. Yeah. So we have matter that will be our anchor, and we add the masks then, and we do parallel block with logits. So we get all the positions at once. Then we do sequential block, which is the nudge. So this created U, that's where it came from. And then we do sequential block of one layer left to right with 4 tiny steps. We get these draft tokens out and we have C. So C is the confidence score. This will be explained later. It's basically telling us before drafter validates anything what it's confident into. And we have then hardware aware, then we have hardware aware prefix scheduler. So it cut where the confidence falls off. So we can see that it's lower here, so it will be cut out. So then we get only the correct tokens. And then we have marker 3, and we are back to the target model. So the target model verifies the scheduled prefix in one parallel pass. So we get off course accepted, then the comma actually get rejected. And because rejection is not a failure, the target model hands back the corrected token. We have the basically decoding step, and we have of course it. And that concludes one full round. So now let's look through how it goes through each step in this example we go through. So we have the Markov head. Basically, matter was our anchor. We have the U1 to 4, and we do the same pass as DFlash makes. So the backbone scores all 4 positions in one shot, and then 4 columns of scores is what we get. And none of them knows anything what happened inside the block, because at that point, nothing points at them. And this part that's not touched this part is the same backbone and same pass. Now we can go further. So we have already the tokens and we are at the cores. So we have the scores from backbone and we add the bias. And then we add sum and we choose the winner. So in this case, cores win. This is explained also here. And here we have the carry on. So each sample token fits the next one. So like this, left to right until the block is full, and that is the Markov part. The bias depends only on the token immediately before it. It's first order like a diagram table. And there is also another technique, which is RRN head, that is described in the paper. Now, what's the cost? Well, for the Quen3, the table we should look for is like 150,000 by 150,000. So that's a lot of numbers. So we basically compress it. And the important part is that we get the latency a bit increased, but we increase the accepted tokens in the versus compared to DFlash. And now let's see what the wire bought. So this is the score for Quen3 from the paper with macro averaged over the domains. We can see that for Quen3, 4 billion, 8 billion, and 14 billion, compared to DFlash, we get 16-18% increase, and compared to Eagle, 30 to 26. So this is accepted length of the draft. And we also have that information that a 2-layer DSpark beats 5-layer DFlash on every domain. More layers made the average more accurate, and 1 token of memory made it correct. So coherence beats the depth. So we'll have both lines draft a block of 8 in one pass, so identical drafting cost. And this is not a speed race between the architectures. The only difference is this tiny sequential head. So now let's watch again how many blocks survive the verification. We have the masked slots. We'll have the drafted tokens, accepted ones and rejected. Let's do it again. So as we see, as it continues, DSpark get more accepted tokens, and it generates more basically with the same cost, with a bit of latency increase actually with this sequential head. But as we saw, it's like 1%. So we have nearly the same cost, more tokens out, and that's the full first fix. So now there is another problem. The blind verification wastes the batch. So let's look. Every token we send for verification occupies a slot in a target's model batch. So when server is quiet, who cares? So this is the case when we have one user like local AI, because the GPU is typically have a lot of spare capacity. We are memory bound. So a wasted verify cost is basically nothing. But under heavy load, and we have hundreds, thousands of concurrent users, every junk token we verify in a slot could have served someone else request. And verifying tokens that are 20% likely to survive is now actively hurting our true output. And we have the scores of tau, so this is accepted length, so how many drafted tokens survive one verification round. And this is from papers. As we see, for code, it's much higher. So the problem is one static verification length is wrong for everyone, and DeepSeek ran production on MT1, so just one drafter, because they have very variable load depending on the users. So it's hard to predict the best value. But like, for example, if you do coding and you know that acceptance length you achieve is higher, then it will serve you better. So this is something that we'll look a bit in the test. So now there is another fix that we need to do and mention. So it's a confidence head. So a confidence head scores every draft token survival odds, and there is a scheduler also that we mentioned before that knows the GPU capacity curve, and it decides how many of these tokens are worth verifying, because it takes some resources. They are typically free because we have low utilization, but as we also learned, in big batches, it's not always free. In this case, we can see that we have EFG, and we decided to verify them because they have high confidence score here, and we drop H because it's not worth the batch slot. And confidence head, it's trained against the true analytical acceptance rate and then calibrated because the neural networks are chronically overconfident. Post hoc temperature scaling takes the calibration error from several percent down to about 1. So we have the prefix scheduler, yeah? So as I mentioned, at serving times, it knows two things: each token's cumulative survival odds and the GPU actual capacity curve. So how true output degrades as the batch grows, profiled once at startup. So this maximizes the expected system-wide true output. So it keeps admitting the most promising tokens from all requests and then stop at the moment another token would cost more capacity than it's expected to return. And as I mentioned, we can see here. So for example, at 22, this is percent value, it's not worth the batch slot. So we drop it before the target model see it and we use resources on it. And it's still loseless because the scheduler stops early. So the decision to admit a token never depends on tokens that come after it. And there is also one thing. So the confidence head takes the hidden state plus the same table row that we already get through Makarov head. We fetch it. So we fix two things. So now let's quickly look why code is better for speculative decoding and math. We look at code. So we have some function here, and we know that the syntax define what will be after it. So we know that, for example, here, meat will have high percentage to be here. But if we have open-ended chat, like how do I stay motivated? Well, we have a lot of options and all of them have good scores, so we can branch easily to others. So as we see here, we'll, for example, draft this, which is wrong because this was the target, yeah? So we have much more branches, so we can go in the wrong direction much easier. And here we don't have as many options, and also in math, yeah, because you have notation, you do some calculations, so you will not start doing completely different calculation after, for example, the one you do. But here with the text, you can do it. You have digressions. You can have digression suddenly, yeah? And also, this is just illustrative value. It's not pulled from paper or anything. So basically what happens, and actually the chat should have much lower start value, but we go, and as we see the code survive more positions, because what it means to survive to position 5, it means to be right 5 times in a row. And as we see for chat, we quickly go much lower. So that's the thing. So small per token gaps become large accepted length gaps, which is the shape of the reported numbers. So we have around 5.2 on code, 5.6 on math, and 3.5 on chat. So it loops back to the collisions, yeah? Because more live branches at one position means the next position average over more words. So basically it will collide more. So we'll also take a quick look at the benchmark comparison because pretty interesting. We have the old version of model here and the new one. And as we can see, the score in like terminal bench, DeepSV is so high, especially here we can see, but we need to also check what the score exactly means. It's pretty crazy for me. I don't remember any model having this big jump with just version update. And as we can see, the Opus 4.8 still win, but this is local model. It's super fast, super cheap, and the cost per task and so on are all things that we can check also on artificial analysis. But at this point, this video is probably too long. But basically, this model is pretty fast, efficient, and it will probably do the task much cheaper, much more cheaper than Opus 4.8 and Opus 5, at least from what I saw from the users. Now we can quickly look at this graph because it's quite interesting. Every dot here is the real traffic on the same hardware, and the blue one is old MTP one, and the green one is DSpark here. So we have two axes, and there's two ways to read it. Across the bottom, we have the TPS, token as user. So this one is how fast one user gets their tokens. Up the side is how much the whole GPU is putting out tokens, and it depends on concurrency. Yeah? So let's now pick the output level and slide across. So we have same views, same box and everything. And as we can see, we get 60% increase for the same output in tokens per user with DSpark. Then also we could get at, for example, 75. So this is with high concurrency, we have 51% of output. And as we mentioned before, we need to have low utilization of servers. So because here we have low utilizations, we see that the values are much higher. Yeah, because as we see here, there's not as many concurrent users serving. So we have a lot of utilization for DSpark, and that's why we get so much boost in the speed. But this is for the very specific use cases that don't happen, because as we know, the DeepSeek actually have problem with serving so many users because their models are so popular now because they're so cheap and efficiently cheap, I would say. These scores we shouldn't care about that much, but these ones are pretty good. And this is another graph that also illustrated well. So we have MTP, as we can see here, and then this. Then we have through output again, and we have number of concurrent requests on x-axis here. And there is also a verification batch. So this is what I mentioned. As we can see, we increase the through output, and in the MTP case, we set it as 1. So it never changed. So the verification budget is the same. But as we explained before, the scheduler see that we have higher load, so it will put less tokens to verify. And this is visible here. So we decrease the verification because we have less available server, not slow down the full process. So that's why DSpark is very useful for high output, because we basically can scale it. It's not like one number that we never change. Now we'll jump to my quick benchmark. Hey guys, so here we have the test that I ran over a few days. So this is quick summary. So as we see, we have 6 settings. We swept one at a time, and every dot is a configuration that was actually loaded and benchmarked on this machine. So Amber is the value that won for me. So I tested 2 file sizes basically, and when I saw that this ran fast enough, I moved to the more accurate one that it will be mentioned later. Then I was checking how many expert layers I can put in the RAM, and then also the drafter location to provide me the best results, and then which guesses ahead there should be. And then also I move with the KV precision, and I start adding more context. So I landed at around this score. I could actually manage 70K and 1 million, but I'm still running needle tests to actually see if there's no issue basically on higher context, because I saw some reports from people running it, but I couldn't confirm it yet because this runs for quite a lot of time and the needle tests. And yeah, so what was the setup? 6000 the Ryzen 9 9950X and 96 gigabyte of DDR5 on dual channel. So the model was 284 billion, and I couldn't fit it in the full GPU, which was also the point of this test, because the question was now how to fit it and what to fit inside the GPU and what to fit into the other parts to get as best results as possible. So first I needed to pick size. So for this I use Anslow guide, and I saw what basically is the share of DeepSeek release to notice the lowest reduction in the quality. So here we have quite a big jump. So I aim in this model. I could technically try this too, but it gave me only like 4% and I wasn't sure about the context. I could pull this model and test it out. But yeah, it takes me one day to basically get this model because yeah, internet sucks. That's what I decided to run. And then to decide what runs on GPU, we have RTX per layer, and there is one flag that decides how many stay on RAM instead of VRAM. So I settled for 19, so 64 gigabytes, and 21 on the GPU, so nearly even split. And everything in RAM, yeah, needs to be streamed to GPU for every token, and this is the full issue if you can fit it in VRAM. So for a rough sense of scale, I work on to basically see how it works. Each token reads around 1.7 gigabytes out of system RAM, which is 32 tokens a second, and it replies something like 50 to 60 gigabytes per second. So this should be the ballpark of dual channel DDR5. And I don't run specific memory benchmark, so this was like more sanity test. So there is also DSpark, which adds basically memory use because it's DeepSeek Speculative decoder, but it's because the model is not small, it's also not quite big for a draft. So it's a small model that gets a couple of next tokens, as we described exhaustively before. So it separates 10 gigabytes of files. So if I feed it in VRAM, it's worth about 3 expert layers. So basically this GPU VRAM could be spent in different ways, basically everything on GPU. And this is the result of my tests. I can put after in VRAM and then the rest in GPU, give me a bit better result. And then the best one is when I put all 21 layers on GPU and then I add the drafter basically on RAM, which was surprising. There was some mention that it could not be the case on Onslaught, but as always, you need to test yourself. So I tested it for a specific use case, which is coding, because that's what I would probably use this model for. So basically, yeah, here is the warning. And there are various benchmarks that you can run. We run synthetic benchmarks on the channel and so on. But the caveat here is that they are bad benchmarks for speculative decoding. And it's also not how you use it, because you typically run something in context and then you fill your context, you start over again. At least that's what most people do, especially for a coding model. So I didn't want synthetic prompt loop, so I use what I use in Ngram to basically see what are the as close to real benefits as possible. So we run multiple turns of prompts, like you are building a full app, to see how it will all basically work. So I built a radio chat app with single Python file, because yeah, it's easier, and for AI at least, and that's will be connecting to llama.cpp server. So basically we do like UI for llama.cpp to add some features. Then we add like history, setting panels, startup probes, and timing displays, speed stats, and so on. Last time I ran it on OpenCode to see if it works, and it didn't, not fully, but this time, yeah, I'm short on time. It's actually takes me a bit more than a week to write everything down and explain. So yeah, here we are. So let's see. And yeah, I have this turn 10 that basically was inflating the scores a bit, because I use it to put everything into memory to get a bit boost, because yeah, sometimes we ask for like rewrites, but I decided to not use it here because it was inflating the results a bit. Okay, so then I ran the test with KV cache, because it of course takes some VRAM, and typically you can use quantization and there is not big issues there. Though I also heard that there are issues there, so I do needle test to basically try it. So in very large basically file, we hide some specific information and see if the model will retrieve it. So this takes a lot of time, because as I can't fit the full model, the prefill is super slow and it's getting slower with longer context, which is typical. But I managed to check it to 512K. It was run on these speeds. We also see there is a bit of difference here, but basically I don't manage to run these two. So I will probably update it in repos down below, or I will write some small note on the llama.cpp like usual, where you can read it in more details than here, because yeah, it's already long. So basically where we land. Well, the generation speed is 31 tokens per second, so it's 15-70% long, much more than Drafter. I also ran the coding accuracy bench to see, but again, takes a lot of time. So I only write a few. The ones that failed basically failed because we ran out of budget because the reasoning was turned on, which is also usual for this type of models. And I shipped with this, but I will probably reach 1 million and just test if it's not crashing. Seems doable. So all of this will be written in the report. I use 3 draft token heads, actually the ones that Unslot suggested. I see that for my specific use case, which is coding, using more will basically slow things down because it's also costly. And as we see, we then decided on the hash type of Q8. So like before, guys, I will not go into much details, but basically all the benchmarks will be down below. This is the Docker, so you can unclick it, or you can do Docker compose like always. This is available through the plugin. Then we can go to the Docker, just a few logs, and we see it's loading the model and it's starting. So that's basically it. You can check all the parameters. I needed to put the model locally, so I have special script because internet is bad. So I need recovery of installation and everything. You can see all the parameters that I have here, all that I set up. I need to disable the automatic VRAM planner because I want to do manual split. And also, I think this is something that I should test more, but I didn't have time, so this will be also in the report. And I use the recommended from DeepSeek parameters for coding, because like we know, all the things depend on it. And there you can access the locally. So that will be it. We are close to 500 drivers. So if you guys like it and subscribe. It actually takes much more of the time that I wanted. And I'm already preparing another video regarding the test of engines and then regarding much more interesting inference stuff. So if you like this type of videos, leave a like and subscribe and see you in the next one.